Objective of our experiment is to study the modulation and demodulation scheme of double sideband DSB amplitude modulation system and obtain their waveforms. Today in this experiment we have a kit for amplitude modulation. This is a transmitter kit. You can see the diagrams are shown. This is a DSB or SSB AM transmitter. So this kit also generates DSB signal and also SSB AM transmitter. SSB is on in our next experiment. We will see. Here today we are going to generate DSB signal, double sideband signal with carrier, and we will balance the carrier or suppress the carrier, and we will see how the wave looks like after suppressing or balancing the carrier. So in AM radio we have receiver also. So we will demodulate this signal also using the receiver kit. This is a receiver kit, DSB SSB AM receiver. There are antennas also to transmit the signal in a laboratory environment. We are using it here because we will see when we are going to demodulate it. We are going to transmit the signal using a wire also, and we will use the antenna also because we need to tune it. Here you can see there is a tuner, as in AM radio also there is tuner. So we are going to send an audio signal here. You can see when we are performing an experiment in a lab, then in real scenario we have information, data, and whatever we want to transmit, we have the data, speech or music or information. But when we are doing it on a prototype like this kit, so we need to have message signal also, so we need to generate the message signal also. So here we can see there is an audio oscillator where we are going to generate the message signal. Here in this block, audio oscillator block, we are going to generate the message signal. Here it is written also modulating signal input. So we are going to generate here modulating signal or message signal, the signal that contains information or data. Well, we are going to see it is a sinusoidal in nature. I have recorded this in one of our DSO. Today we are using two DSOs. I have recorded this modulating signal on a DSO, as well as after modulation the DSB. This is a block of our balance modulator and band pass filter. This is a modulator block. Output of this DSB output, you can see DSB output. From here we can see the DSB output, double sideband with carrier, and we will see how we can balance the carrier. This is a balance switch. When we will balance it, we can get a particular suppressed or balanced carrier. So we are going to see how DSB SC look like, suppressed carrier, double sideband suppressed carrier. For a modulation we need an information signal as well as the carrier signal, because carrier signal is needed to shift the frequency of a low frequency signal to a higher frequency signal. It has so many advantages, because antenna height also gets reduced. We can transfer to a far place, and so many other advantages for transmitting an amplitude modulation signal to a distance. So we have carrier generator here. We have carrier generator 2 and we have carrier generator 1. So we have carrier signal here. It will generate a frequency of 1 megahertz and 100 millivolt peak to peak. So we have a carrier signal and we have a message signal also. Message signal has frequency range of 300 hertz to 3.4 kilohertz, and it has peak amplitude 0 to 2 volt peak to peak. There are two knobs for given in audio oscillator block. We have one knob for frequency and one knob for amplitude. We can change the frequency of audio signal that we are going to generate, or a message signal we have here, and we can also change the amplitude. We will see when we are going to plot the waveform of DSB, then we will see what is the effect of this knob if we are turning it leftward and we are making amplitude 0. Amplitude 0 means we are not transmitting any signal as a message signal. And we will also see what is the effect of frequency if we are changing the frequency of audio oscillator, because when frequency is getting changed, FM is getting changed. If I am increasing the FM, and I am decreasing the FM, then the bands will get more separated, because we will see when we are going to see the plot of this DSB signal. Here are knobs actually. We can select it for DSB and SSB. I have selected it for DSB. If I pin it down, it will be for SSB. So today we are performing double sideband, so I have put the knob on DSB. There is this block for audio inputs. This is audio input select. When we have an external audio, as I am speaking, if I want to transmit the speech signal that I am speaking, the audio signal, then I can use a mic and attach it here, and that will be external audio input. Since we are using the internal audio input from this audio oscillator, whatever we are generating here in this prototype kit, we are using this, so I have kept this knob to this audio input. We are taking it from this particular inbuilt audio input. Okay, so this knob is for this is for DSB. And here you can also see there is a knob for we have an output amplifier and gain adjustment. This knob is used for gain adjustment. If you want to adjust the gain of the signal that we are getting as an output, transmitter output, after amplitude modulation, then we can adjust this gain. Before it, you can see either we are using DSB or SSB. Today we are performing from for double sideband, so I am using it DSB. If I put it down, then it will become for SSB. Yeah, you can see this. So there is a transmitter output here. You can see there is transmitter output here. This output will get transmitted. We can use here two modes. Either we are going to transmit it using an antenna. You can see this antenna. I'll put it down so that you can see. This is an antenna. Using this antenna we can transmit the signal. Then we need to put it on antenna mode. Here I am using the socket mode because I was performing the experiment using the wire transmission. We will see I am going to transmit it using a wire and as well as through antenna. If I need to transmit it through antenna, then I need to switch it on to antenna. So there are some of things. I have explained the basic things. So up till this we have an audio oscillator that is going to generate audio signal, message signal. We have a carrier generator that will generate a carrier, and we will use this balance modulator. This is an amplitude modulator that is going to take FC from here, FM from here. Both are getting modulated here, multiplied and getting modulated. We have a band pass filter, and we are going to balance it and see how it is DSB with C and DSB without C or suppressed carrier, DSB SC and DSB AM. So we are going to see both the signal. I have recorded this message signal and DSB with carrier signal on one of our DSO. I'll show this. This is the waveform. This is a message signal we have. I'll show how we can get this output in a couple of minutes. This is our message signal, and this is DSB with carrier. This is a double sideband with carrier. So you can notice that here we can see this is a voltage maximum and this is the voltage minimum. So if you want to calculate the percentage of modulation, then you can use the formula for percentage of modulation using Vmax minus Vmin upon Vmax plus Vmin. If you are we are getting this Vmin to 0, then we are going to suppress the carrier completely, or modulation will be 100% or perfect modulation. This is under modulation. We will see three cases. This is under modulation. We will see perfect modulation, and we will also see over modulation. That means modulation index will be greater than 1. Modulation index less than 1, equals to 1, and greater than 1. All the three cases: under modulation, perfect modulation, and over modulation. This is a case where we are under modulated the signal, and we have plotted here. I have recorded it. You can see here it is in stop mode. I have stored it, and just to show you, this is a message signal and this is our DSB modulated signal with carrier. We will see how we can balance the carrier using this balance knob. So I am going to show you some of inputs here on our other DSO. I'm I'm going to connect this DSO only. Let's see. I'm using this probe, 2 probes, and both the channels of DSO. Make some adjustment and see. This is a recorded signal as it is stopped at stop condition. So I'm going to run it and I'll show you how the waveform looks like. I'm using this particular ground here. This kit has ground here. I'm using this for ground. All the black probe of DSO will be connected to the ground. So I'm connecting both the black probe of DSO to the ground. You can read it in your manual also. The steps are given completely in proper manner. You can read it from there. The steps that I am following, you can read it in parallel and follow the same step. So I'm going to see, this is the message signal. I'm connecting it here so that we can see our message signal. I need to switch it to DSB. I need to switch it to internal. Yeah, this is internal. And this is our DSB output. I'm going to run the system so that we can see. You can see we are getting the same as I have recorded it. It is in run condition and we are getting this is a message signal and this is our DSB with carrier. We are going to see how we are going to balance the carrier and get perfect modulation. This is the under modulation case. Now you will see I am going to balance this. If I will balance this, then that particular waveform will change. I am going to turn this knob. You can see in the DSO, if I am turning this knob, you can see the Vmin is getting reduced. We'll turn this knob so that Vmin gets 0, till Vmin gets 0. Now this is a condition where Vmin is almost 0. Since Vmin is 0, I'll stop this so that we can see it. I will stop it. This is a condition where we are getting DSB with suppressed carrier or carrier is being balanced here. This is a perfect modulation case. This is a perfect modulation case where Vmin is 0. If you put in formula the Vmin equals to 0 in your depth of modulation, then you get modulation index equals to 1, that is perfect modulation. So we have seen this case. We already have seen the first case, under modulation. This is the perfect modulation. We are going to see how this is going to be over modulation, means modulation index is greater than 1. I'll change this balance knob again so that we can see. I'll run it first so that it can get. I'm turning it leftward so that we can get under modulation. You can see here. You can see here in the DSO. I'll stop it so that you can see it. You can see. This is our modulating signal that we have given, and this is under modulation case. This is under modulation case where over modulation case, modulation index is greater than 1. We have over modulated the signal and modulation index is greater than 1. So we have seen 3 cases: under modulation, perfect modulation and over modulation here. Message signal is same in all the cases. Now we will see what is impact of amplitude. If we change amplitude of our message signal, then how the signal is going to get affected. I'll show it for DSB C with carrier 1. I'm going to make it first DSB C. This is, I'm turning it right so that it will become DSB C. We have both Vmax and Vmin here. You can see we have both Vmax and Vmin here. I have stopped it so that we can see it. This you can see the first case, under modulation with carrier, one the perfect modulation case where we have balanced the carrier or suppressed the carrier. Now I'll show you how what I was saying about if we change the amplitude, then what happens. Now we are going to change the amplitude of message signal. I'm turning it to run run mode, so that whatever effect I am going to make, that will reflect on the DSO. I am going to change this amplitude. I am turning it to 0. Let's see what we can see. If I am turning it to 0, you can see here there is no message actually. Message signal is 0 volt, so there is no message, so only carrier will be there. If I'll show you, I need to make it like that so that you can see, because carrier signal is of 1 megahertz, so I need to change this particular thing to there. I will stop it so that you can see. This is only carrier signal. We have only carrier signal. So the waveform we were at was DSB with carrier. DSB with carrier. I have reduced the message signal to 0. So we are having only carrier signal. We don't have any message signal here right now. So I'm going to change the amplitude little bit so that we will see. I'm going to give amplitude here, and we will see how. I need to change the knob because I have changed it. I need to auto scale it so that I can see. Yeah, you can see I have changed the amplitude. Whenever I am changing the amplitude, this Vmax and Vmin is changing because AM is changing. Amplitude AM, the amplitude of message signal is changing, so this Vmax and Vmin is also, Vmax and Vmin are also changing. You can see here. This is our DSB signal with carrier. I'm going to make it, I'm going to change frequency here. What I was telling you, if I'm going to change the frequency, then there will be change in the bands will get shifted. The upper band will get shifted or lower band will get shifted. Because if you see here, this is a DSB signal, frequency plot of the DSB signal. If I am changing this FM, if I am increasing this FM, then FC plus FM will get increased, it will move rightward, and FC minus FM is getting increased, then it will also move. So if we are changing frequency of this message signal from this audio oscillator, this knob, if I am changing this frequency, then these bands will move apart or come closer. So I am going to change this frequency, and I will show you how the bands will move apart and bands will come closer. You can see here DSO, on DSO I am changing this. You can see here, if I am changing the frequency, I am reducing the frequency. Let's see. You can see this is moving apart. You can see I'm reducing the frequency, then the bands are moving apart. You can see if I am increasing the frequency, then bands are moving closer. You can see the change in frequency of message signal. As frequency is getting increased, the waveforms are coming closer, and in a very similar way the bands are also getting closer and apart. So you can see whatever, if we are using these two knobs. If I am changing this amplitude, then you saw the effect. If I am changing this amplitude, then you saw the effect, because it is affecting the depth of modulation also, because Vmax and Vmin is changing. If I am changing this frequency, then you saw it clearly that the bands are moving apart and closer. So we just have seen this effect of this both knob, frequency and amplitude. We saw how this modulated output look like, and how we can balance the carrier signal, and we are going to get perfect modulation. We saw all the cases. So that we have done the modulation part. This is a modulated signal, and this is our particular message signal, the audio signal. This is with carrier. We saw a couple of minutes back how the carrier can be suppressed and 100% modulation can be achieved, or over modulation, under modulation and perfect modulation. All the waveforms we have seen. Now it's a part we need to transmit the signal and receive on the receiver and demodulate the message signal, and see if we are getting the same message signal or the same audio signal that we are sending here from the transmitter block. So I'm going to the receiver part of this trainer. You can see at receiver part we have the antenna to receive. This is the antenna to receive. We have here two select inputs. If I am taking the input from antenna, then I'll put it to this mode. If I am taking it from using a wire, I'll show you both the cases, because we need to tune it very fine. So it takes time to tune it to the particular frequency. And you can see here when we are transmitting an amplitude modulation signal using amplitude modulation technique, an audio signal using amplitude modulation technique, then we need to use some transmitter. When you design a system for a hardware system for this, then you will come to know there is frequency up conversion needed over there. We need to design an intermediate frequency for 455 kilohertz, for which transmitter used to come in the market. You can purchase and use this transmitter to transmit and receive the signal. So here what we are doing, we have an local oscillator. Here we have a local oscillator. We are using this mode to internal, so we are generating the signal from local oscillator in order to for this intermediate frequency block. So we will tune it so that it will change the frequency of local oscillator. We are going to tune it. And how we are going to sure about that we are receiving the signal or not? There is an audio headphone. This is a speaker system. If I'll change it, the output from this to audio, you can listen. If I tune it, then you will listen the sound. The first tone frequency we are going to listen, that will be our notice to see how we are. If I am changing this to antenna, because we are going to receive through antenna, so I am changing it to antenna mode. You will see there will be a humming sound. You can see, you can listen it, that there is a humming sound. When I'll tune it so that we can get the first tone, then we can assure that we are going to receive the signal. We need to finely tune it. We need to tune it very fine so that we can listen to it. I need to make it antenna so that we can receive it. There will be a there will be a sound of single tone that will clarify that we are receiving the signal. What I was trying to tell you, that this speaker, we are going to see a tone frequency. We are going to hear this tone frequency. We can use here a headphone also. I was using headphone for it. We can use here headphone also to hear the signal, so that we can clearly see clearly hear the single tone frequency, the first tone frequency, so that we can assure that we are receiving the signal using this antenna. What I am going to perform here is, first we are going to assume that whatever we are transmitting, we are going to receive at receiver, and then we will see how demodulation take place. There is a diode detector where R and C values are going to get decided by this knob. If I am changing this to a particular RC value, so that we can use envelope detector or this to trace the wave, to trace the message signal, to identify the message signal, to identify the audio signal that we are transmitting. Now I am changing this both to the socket.